So today I'm going to talk about topics which are not deep learning. So I think maybe a good break for some of you. And whether it is deep or shallow, I will let you be the judge of it. But at least what I can say that it's a topic which I have worked on since my PhD. And in fact, when I finished my PhD in Berkeley, I had left something open which I didn't really like. And I think I'm getting closure on this topic 20 years after. So good take-home message. Always keep some problems in the back of your head. Sometimes you find new toys and new tools, and you can provide new solutions. So today I'm going to talk about information theory and kernel methods. So as a disclaimer, it's not ready for deployment yet in large-scale applications. Okay, so the idea is more like defining new sets of tools that hopefully will be useful, but as of now, they are implemented, but not in large-scale settings yet. So also, feel free to interrupt me during the talk. I think since we have some time, I'd like to keep it as interactive as possible. All right. So what would be the goal? The goal of today? The goal of today will be to measure distances between distributions, between the probability distributions. And this comes out in many places throughout machine learning, data science. And so here are a few examples which I'm listing. Like a classical one is model fitting. So you minimize the distance. So here distance will be in quotes, okay, that are maybe not metrics. The distance between the empirical distribution in your model, and you get model fitting. And most generative modeling techniques end up being of that kind. You minimize some distance, and the choice, of course, you have to choose the correct model, but also the correct distance. But sometimes you may want to measure independence. For example, if you want to do feature selection, you want to measure independence between give the feature some variable in the label. Also, in other setups, when you add noise to data, for example, for privacy issues, you may want to measure how much you lose when adding noise. And also when you want to quantify uncertainty. So this comes up in many places, having distances between distributions. So why is it difficult? It's difficult because we are not dealing only with Gaussians and discrete random variables. So if you have Gaussians, then everything is easy, okay? If you have discrete random variables with only a few outcomes, it's also easy. You compute the probability mass functions and you look at any book and you use the distances. Okay, the difficulty is that we want to apply this to continuous sets with obviously nonlinear dependencies. Okay, so this is the key difficulty. The other difficulty is that we want a distance which you can estimate from data. Okay, so this is the least we can hope for a machine learning application. And what I would like to add today is I would like to have some physical or statistical meaning to the distance. It's not only a number; it's a number which I can give to an engineer, and the engineer will understand what it means. And I come to that in a moment. So for doing this, there are many ways of doing it, and I will review three classical frameworks. The first one is classical information theory, okay, where you so this is for a finite number of outcomes. You take P and Q being defined by the probability mass functions, and you sum P log P over Q. This is the classical Kullback-Leibler divergence, which is non-negative and will will be zero if only if P is equal to Q. But it has more than that. It has some nice invariant properties by reparametrization, and it has strong physical interpretations. Okay, so as in terms of communications, like number of bits to encode P with Q or Q with P, I always forget. Also, it has some strong link with probabilistic inference, okay, through duality. I will come back to that later in the talk. But the issue is that for discrete problems, it's very simple. But as soon as you move beyond discrete or Gaussians, then this is going to be more problematic. Then another slightly more recent in its like wide use within machine learning is optimal transport, where the idea that you compare two distributions P and Q by moving mass from P to Q and trying to minimize the distance that you have to move. So this is somewhat physical because you have the distance D, but I've asked around, and it's unclear what the meaning. So people use this a lot to do algorithms, and so, but the meaning of the value is still a bit unclear. So of course, Perret and Couturier did not invent this, but there's a nice book explaining like various applications. So what I will mostly focus on today is looking at distributions like distances based on moments. Okay, so what the moment is I have a feature map phi that goes from my input space X to some Hilbert space H. So you can think of H as being RD if you wish, but D will be infinite in a moment. And I'm characterizing probability distributions P on X through the mean element, which is just the expectations of phi under P. So mu P will be the mean element. So typically, if X is in R, you can put in phi of X, 1, X squared, and you get the classical moments. So what is nice about this is that if you include, it's well known, if you include sufficiently many moments, then you will fully characterize the distribution. So if mu P is equal to mu Q, then P has to be equal to Q. And this has led, particularly if you use the Hilbert space structure and the Hilbert norm, to the classical maximum mean discrepancy, which is essentially the norm of mu P minus mu Q. So why is it nice? Well, first, it does characterize distances. So this is, you can do learning with this and be consistent. Also, if you only know mu P or mu Q, P or Q through RID samples, you can estimate with convergence rates in 1 over root n. So you don't see here the curse of dimensionality, which you see in many of the other distances. And if you want to work in high dimensions, okay, with D being very large, and if sometimes potentially infinite, because you only need the kernel K of xy, which is the dot product between phi of x and phi of y. Okay, so it's very nice. There's a good tutorial paper by Muande and colleagues, and this very much like all distances between probability distributions. There are applications in model fitting, independence tests. You can do GANs if you want with them. But what I've always felt unsatisfying with those like distances is the link with any form of information theory or physics. Okay, so you compare moments. Okay, so if you put like x squared and x cubed, okay, sure, it does characterize the distributions, but what does it mean? Okay, what does it mean to have a value of 0.1 for that distance? Okay, so the goal of today is to try to extend that type of framework, so based on moments, and have explicit links with information theory. So the summary of what I'm going to talk about is on those 2 slides, or maybe one. So the idea is to go one level up, so not consider only moments of phi, but moments or expectations of phi times phi transpose. So here, phi star will simply be phi star is the rank 1 matrix if you're in the infinite dimension, whose elements are ij is phi xi and phi xj. So it's a rank 1 matrix. If you are in a Hilbert space, it's an operator, but let's see it as a matrix. Essentially, the uncentered covariance matrix of the feature phi for the distribution P. So we know nice things about that matrix. It's always like symmetric or positive semi-definite. And we're going to not use a square norm between sigma P and sigma Q. We could use the Frobenius norm or the Hilbert-Schmidt norm. But we're going to look at quantities which are closer to information theory. And in fact, we will use quantities coming from quantum information theory. And we'll start with the von Neumann entropy. which I will define precisely later, the trace of sigma p of sigma p, and the associated relative entropy. And once you use those quantities with that definition, then things start to be interesting. Okay, and see the topic of a paper which is now published at the attribute transactions of information theory. And what I'm going to describe now in this talk is, first, it has a direct relationship with information theory. It's not simply it looks like it. That's a strong link, maybe like a lower bound on the true quantities. But then you preserve the nice things about like the maximum mean discrepancy, MMD, by having estimation in 1/n. And I will show how can this be used in multivariate modeling and also in variable inference. So this is the plan for today. And if you want to know more, you can simply look at the online preprint. All right, so let's go down to the various definitions. So I'm going to consider a positive definite kernel, K, defined on X times X. So here, also one of the goals, which I forgot to mention, is that X can be anything. And it is the beauty of a kernel method, is that X can be discrete, X can be RD, X can be the set of graphs, X can be an image, X can be anything. I will provide examples in RD because it's concrete, but this is a way to extend information theoretical quantities to any set. So we characterize everything for the kernel, K of XX. So your PSD, your positive definite kernel, if all the pairwise, the metrics of pairwise evaluations are all PSD, and we're going to assume X is compact and the features are normalized. Okay, so all the features have norm less than 1. So it's known that as soon as you have a kernel, you have some feature map phi of X. Okay, so I could have started from phi and defined K, but here I chose to look at K and define phi. Okay, as soon as K is a positive definite kernel, you know there exists a feature map phi that goes from your input set X to some potentially large Hilbert space, so that K of xy is phi of X times phi of y. Okay, so this is, if you prefer, I could have started from phi. I start from K because since I want to consider phi being infinite dimensional, I don't want to compute phi. So I will only access phi through the kernel metric, so the kernel. Then what is typical in that setup is to consider the space of linear functions in phi. So f of X would be f dot product with phi of X. So it's a function of X, which is linearly parameterized by f, and that defines functions on the edge. And this is what people typically use in kernel methods. Okay, and for those, for that set of functions, it's the kernel is said universal if that set of function is dense in the set of all functions. Okay, all continuous functions with uniform norm. And essentially all like the classical kernels, like Gaussian kernel, exponential kernel, and so on, do satisfy that. So for those kernels, phi is infinite dimensional, okay, and you can characterize all functions. So as I've mentioned, the Gaussian kernel here is infinite dimensional, but we will consider other kernels as well today. What will be important is the notion of scale, sigma. There's often kernel come from the notion of scale, okay, depending scale the input space, and sigma will be the length scale associated with our kernel. So let's give some other concrete examples, and to me this is the one which is my main motivation because everything is easy for this one. So if you take like the cube, the torus 0, 1 to the d, and you consider like translation invariant kernels, then you can, everything is defined through the Fourier transform. And here, because we're on the torus, it's a Fourier series, so indexed by omega being having integer values. And if you take that kernel, you can see that kernel as phi of X times phi of Y for that phi of X. So the feature is indexed by all integer vectors, okay? And this is just a complex exponential. They are missing a 2 pi here, sorry. There's a complex exponential here, plus times a scaling vector. And that scaling factor And that scaling factor is here to make everything sum to 1 or be less than 1. Okay, so if you compute the norm of phi of x, the square norm of phi of x will be the sum of all q hat of omega, and we're going to assume this is less than 1. So essentially, we're going to consider like infinitely many frequencies. The cool thing here, now you can look at what the covariance operator is by computing the element omega omega prime, which is obtained by omega omega prime here, and I see appearing so q hat of omega prime coming from omega prime, and by using the fact that I have complex exponentials, I get the expectation of a complex exponential, and this is the classical characteristic function taken at omega minus omega prime. Essentially, that moment you get all the characteristic function, not coded at a line, but coded through in a PSD matrix. Okay, so it's a particular way of displaying and storing the characteristic function. For example, you can typically compute Q for many Q hats. So if you like to have exponentially decaying spectrum like this, you can compute K. You can compute Q directly. But this applies to any set, and I think finite sets are also important because they provide intuition for what we want to do. And if you use a finite set with a so-called one-hot encoding, so if your set has a K element, then you map your data in a RK by sending each label to one element of the canonical basis. And then you can check that phi of x transpose is always diagonal, okay, with a 1 exactly at the corresponding index of the canonical basis. And then you end up simply encoding the probability mass functions on the diagonal. Okay, so this is important here. In the simplest setup, finite data, we are just doing a very fancy way of storing P into diagonal of matrices. But we'll see that this will be crucial in a moment. So some properties of that covariance operators. So first, it is positive semi-definite. It's straightforward from the definition. Phi star is a PSD. So the trace is less than 1 because I've assumed that the norm of phi is less than 1. And because I have a trace class operator, I have a sequence of eigenvalues going to 0. And since I've assumed, and I will assume it from now on, that the kernel is universal, then the mapping from P to sigma P is injective, essentially in the same way as the mapping from P to mu P was injective. Okay, in fact, this is just mu P for a particular feature. Okay, so this is just like replacing the kernel by the square kernel. Okay, so everything which is true for the mean element will be true for us. Okay, at the moment, I have not used the matrix structure of the problem. Now, let's now use this matrix structure, and let's define the negative entropy. So this dates back from Neumann in the 30s. And so we're going to consider a spectral function. So the trace of A log A is simply computing like lambda log of lambda for all eigenvalues of A. So this applies as soon as A is diagonalizable, so A being symmetric or Hermitian. We assume that all the operators or matrices are positive, so log lambda is well defined. So give me an operator or matrix A if you know the eigenvalues, and there may be infinitely many, okay, if you're in the kernel case, then you sum lambda log of lambda, and you get the von Neumann entropy. So here you can check that if you take A being Jack P, if you take that case, okay, so the eigenvalues of sigma P are just the diagonal element, and the sum of lambda log lambda is simply the sum of P log P, and you get the regular entropy. All right. Now, first, this is a convex function, okay, because the trace of f of A, when f is a convex function, is always convex. Okay, so with a convex function, so it's differentiable, it is strictly convex, so we can define the Riemann divergence. And this happens to be the relative entropy. Okay, so it's not obvious. So you have to take C of A being the trace of A log A, compute the gradient. So you have to know about the gradient of spectral functions. Essentially, it's log A, and then log A plus some constants. And then you compute the Riemann divergence, and you get something like that. And in our situation where often things will be normalized, the trace of A will be 1, and the trace of B will be 1, and you recover a trace of A log A minus trace of A log B. And this starts to look a bit like the sum of P log P over Q. So a few properties of that relative entropy. So this is very well studied in the quantum world. Like most of the results come from quantum physics papers. So some of them are obvious coming from a convex optimization perspective. So the fact it is like non-negative, it's obvious because it's a Riemann divergence. So it's always non-negative. It's equality. You have equality if A is equal to B is also obvious, but a direct consequence of being a Riemann divergence. So this one is simple. The convexity in A is also a straightforward consequence of the definition, because all Riemann divergences are always convex in the first argument. What is not at all straightforward is the fact that it is jointly convex in both A and B. Okay, so this is totally non-trivial. The proof, okay, there are many proofs. I've put one in my paper, and the proof is interesting, but totally non-straightforward. And for those who like optimization and probability, this is used a lot in the very nice tutorial by Joel Trop on matrix concentration inequalities. So for all of you who have ever used any of those inequalities, they are based, okay, on this joint convexity of this relative entropy. And very nice book and very nice set of results. And this is also often used in optimization as the way to do smoothing of the eigenvalues, and also nice paper by Venkat Chandrasekaran and colleagues. But today it's not about optimization of our statistics. It's about applying this to my covariance matrices. All right, so let's do what I said I would do. So I'm going to define the kernel relative entropy as this quantum thing on sigma p and sigma q, where sigma p and sigma q are the covariance operators. Okay, so this is that's how I see some protests outside. They want to get in. Interesting. Are you still following me, or? No?
It seems so.
Okay. So let's move on. Okay. So so you take sigma p and sigma q, which are your covariance operators for P and Q. You just apply the formula of the von Neumann relative entropy, and this defines some notion. Okay, this is simple. The question is, what does it do? So a few properties. First, this is well defined if P and Q are reasonably nice. So for example, if you have some derivative you have a bounded density of P relative to Q, you're finite. It's always non-negative by construction, and it's always zero if only if this is zero, and this is zero if only if sigma P and sigma Q. And because I've assumed that I know the mapping from P to sigma P is injective, this is only equal when P is equal to Q. Okay. One nice property that it is jointly convex in P and Q, and the reason is because D is jointly convex in sigma P and sigma Q, and since sigma P and sigma Q are linear in P and Q, you preserve joint convexity. So those are the simple properties. But what I want to focus on is on relationship with information theory. Oh yeah, also if you prefer to have no entropy, okay, then you can do it, but you have to be careful with normalization. And so I'm not going to cover it today. You can see more details in the paper. All right, so maybe a spoiler. I will present many similarities with the classical Shannon entropy, but there have to be a difference, okay? Because if I share too many properties with the Shannon entropy, I have the Shannon entropy. Okay, so something will break down, and I will come back to that later. So let's look at what it is for my example with the finite set with orthonormal embedding. So remember that for that set, sigma p is simply diag of sigma p. So everything is diagonal. So another way of putting it is that all matrices can be diagonalized in the same basis. So all those like log of matrices will be easy to do. And then the relative entropy is exactly the classical Kullback-Leibler divergence. Okay, so it's important that if I use orthonormal embedding, this is only true for orthonormal embeddings, where if x is equal to y, the norm is phi of x times phi of y is 1 and 0 otherwise, then I get the exact entropy. The question is, will it be true beyond finite sets? And it won't be true, but it will be, I will replace this by some bound. So let's prove that result, okay, that this new quantity d of sigma p sigma q is a lower bound of the true Shannon relative entropy. And the proof will fit in one slide, and it's quite simple, and suggests an application of Jensen's inequality. So this is the definition of d of sigma p sigma q. This is sigma p. This is sigma q written as an expectation over p times the Arnold-Nikodym derivative of q with respect to p. Okay, and now what I have is I have a convex function taken at an expectation here, an expectation there, over the same distribution p. And because I'm jointly convex, I can use Jensen's inequality and get this inequality. So I get the expectation over p of what is inside there, pum, and what is inside there, pum. Okay, so for this, I do need the joint convexity with respect to the two arguments. And once I have that, I start to be in good shape. So why am I in good shape? Because now I get two matrices there and there. And this one now is rank 1 with all eigenvalues equal to 0, except 1 equal to the square norm of phi of x, and the eigenvector is proportional to phi of x. And this one is just the same, but rescaled by a positive number. Okay, so now I can look at all the 0 eigenvalues. They will not count because I have lambda log of lambda, they all disappear. And I just have to focus on the eigenvalues associated with phi of x. All right, so I have those two matrices, and now this has eigenvalue phi of x squared. Okay, this has eigenvalue phi of x squared times dq over dp. And now I'm just using the fact that the volume entropy is trace of a log a minus a log b. So this is a log a part in blue, and the minus a log b, this is the blue part with the green part over there. This is just an equality here because I'm just applying this to that along the joint eigenvector for the two matrices. And now I'm done because I can cancel phi of x, okay, and I can use the fact that phi of x is less than 1. And I get that all the phi of x disappears, and I get the integral of p of log of dp over dq, which is exactly the Shannon entropy. Okay, so here I've shown that I get always a lower bound on the true entropy. And the key here is to realize that there are no assumptions except this one. I need normalized features, okay? And apart from that, this is always true. Okay, so this will be true for all kernels in the whole setup. Of course, and I will come to this now, is that there are some inequalities there. So this one is not really a problem because often we use normalized features, so you get equality there. But you get, like, of course, an inequality there by Jensen's inequality. And in the paper, we look at the I look at the equality situations, and you can check the paper if you want to know more. And the question is, how tight is it? Okay, because I know a very simple lower bound of the entropy, which is 0. Okay, so 0 is less than dpq, and 0 is not very useful as a lower bound. Okay? So let's look. And so here, I'm not going to give like all the details because the proof is not 2 lines anymore. Well, it's only 5 lines, but I won't do it on the slides. And what you can show is that, so if you take now P of Q, now you have to put some assumptions. So for simplicity and to make my life simple, I'm assuming like strictly positive densities with respect to a joint uniform measure of some kind. And then I can show that the difference between D of PQ, which is the true relative entropy, and the new one, is always non-negative because of the previous slide, and is less than a product of 2 quantities, one which is depending on the regularity of P and Q, and one which is the quantity characterizing how far the embeddings are from orthonormal. Okay, so the quantity is there's a quantity, it's like can check in the paper. And of course, when phi is, you get totally orthonormal embeddings, delta is 0, and I covered the equality from 2 slides ago. But you please provide some bounds. So I had a proof for that, which was like 12 pages long and with like lots of constants. And I realized that you could get like a direct proof using quantum information theory directly, using the fact that for quantum systems, you do have a form of data processing inequality. And by using this form of data processing inequality, you can derive a bound like that, which you get very, very in a quite simple way. So if you want to know more, you can look at the paper. So for my examples in the torus in dimension D, so what do you get? So what you can check, you can compute the various quantities for the essentially a kernel with a length scale sigma. Okay, so then you can show that the difference will go to 0 as sigma goes to 0. In a sense, that's normal because when sigma goes to 0, x minus y over sigma will tend to either infinite. So will be this will be infinite or 0, and since k is typically decaying, the kernel will be either 0 if you're different and 1 if you're equal. So when sigma goes to 0, typically takes a Gaussian kernel. When sigma goes to 0, you end up going closer to orthonormal embeddings. So you get a dependence, which is and the decay square, and the semi-surprising fact is that it doesn't depend on dimension. Because the distance, the big O, has dimension factors, but not the dependence in sigma. So now we know we have a reasonably close approximation. Now can we estimate it? Okay, so now we know we have a link with information theory, but this relies on computing eigenvectors, eigenvalues of infinite dimensional operators. This starts to be a bit like complex, but can you estimate from data? And the answer is yes, using like classical algorithms. So the idea is to estimate the whole thing. I will only focus on the difficult part, the trace of sigma p log of sigma p, and because it's already interesting. So now we're going to be very non-creative here. We're simply going to replace sigma p by the natural estimator of sigma p, which is sigma p hat, which is the empirical covariance matrix. Okay, if I have data x1 to xn, which are ID from P, I just take the empirical average. I call that sigma p hat and just replace sigma p by sigma p hat, and I hope for the best. So the first nice part is that you can compute it, okay, because sigma p hat, it's still an operator in infinite dimensions, so it's still hard to compute, but it turns out that in exactly the same way as for kernel PCA, the eigenvalues of sigma p hat are exactly the one of k over n, where k is the kernel matrix, which is n by n. And so this means that the Boltzmann entropy of sigma p hat is the one of k over n. So now you need simply to compute the eigenvalues of the kernel matrix and compute that quantity, the sum of lambda log of lambda. So it's still like it's not fast, and it's n cube, but then you can rely on like 20 years of algorithms in kernel machines to lower this from cubic to n with many various techniques, particular column sampling. Right, so we can compute, fine, but does it estimate the correct quantity, which is not totally obvious because sigma p log of sigma, when you have sigma p log of sigma p, you have the log of lambda. Okay, so when lambda goes to 0, then this may blow up. It turns out it doesn't, and so there is one quantity which is controlling the convergence rates. So for the experts in kernel methods, then this is often called the maximal leverage scores. Okay, for the regularizer with the regularization lambda. And essentially, the quantity that controls estimation performance is the integrity leverage scores, and it turns out that this quantity is finite as soon as the decay of eigenvalues of sigma is strong enough, typically 1 over k4, something like that. So this is like this show that if you have a reasonably strong decay of eigenvalues, then everything is fine, and you get like an estimation rate in 1 over root n, which is nice because you don't see here the curse of dimensionality appearing. Okay, so C is the constant. The C will depend on, and I will show in a moment, C will depend on dimension, but the rate of convergence, the power in n does not. One surprising aspect is that at least to estimate trace of sigma p log of sigma p, you don't need to regularize. So I don't exactly, I was a bit surprised when I saw that, but well. So let's look at the torus for my, just to make things a bit concrete for that particular example. So then you can compute C, and C is of the order sigma to the minus D. Okay, so now you pay a price for sigma. So remember that if you want to approximate the true relative entropy, you need sigma to go to 0. So C will explode. Okay, and now, so if you put sigma over there, okay, then you get an estimation rate proportional to this. So there is a mistake. It's a sigma to the minus D here. I don't know what's happening. So I should correct. Sorry about that. And now what you can play, you can play games by trying to see which sigma you should use if you want to estimate the true entropy. So we have a bias of sigma square, or the variance of that. So if you choose sigma correctly, depending on n, you would get an estimation of the true entropy. And if you do that, you end up with a rate which is power of n, the minus 2 over d plus 4. So now we see the curse of dimensionality because we get the 1 over d. It's not optimal, okay? So for the same assumptions, like regarding regularity, you can show that the optimal thing is a square of what we have. Okay, so we are not optimal, but I was pleasantly surprised that my goal was not to estimate the true entropy, but to recover something which is reasonable. Right, so like a very basic simulation just to show that this can be run, at least in dimension 1, and there are others in higher dimensions, but in 1 it's easier. So I'm increasing the number of samples. So classical, like verification of your theorem, you increase the number of samples. You look at the entropy estimate. In black, this is a true shell entropy. And in blue and red, it's here with two values of the bandwidth. So a large value, a small value. With a large value, the convergence to the n infinite is a bit quicker than for smaller value. It is consistent with the bound. If you look at where they converge, they get more or less close to the true entropy. So of course, with large sigma, you're further away. That's normal. So you converge quicker, but further away. And you converge from above. So this is just like a consequence of James test inequality. And so you see that you do get estimation of the entropy when you get more examples. All right, so now let me move on to what we can do with it. Okay, so now what we have something which we can compute to measure distances. So at this point, wherever you are using MFD, you can use this one instead. I don't believe it's going to change much in the performance, but at least the value that you will get will be a bit more calibrated with respect to entropy. And this has been used by people for differential privacy to get a handle on the true loss of a true lot of information. But what I want to focus on for the last part of the talk is on other applications, what we can do with it. And the first part is essentially, this was my PhD thesis 20 years ago, on trying to measure, to characterize independence between random variables. And so what I was doing, and which is not what I'm doing now, what we were doing with Mac Jordan like 20 years ago was essentially to, you take sigma p and sigma q, and we're essentially using the Gaussian entropies of sigma p and sigma q. What do I mean by Gaussian entropies is considering that sigma p is the covariance matrix of a Gaussian with mean zero and variance sigma p. And then if you do that, okay, so if you do that, the von Neumann entropy, you don't do this, you end up with 1/2 of log det of sigma p minus 1/2 of log det of sigma q plus 1/2 of trace of sigma p, sigma q minus 1, or a variation of that. And you get log dets and the classical like maximum likelihood type of formulas for Gaussians. And if you do that, you don't get what I'm showing here. There's no upper bound, lower bounds, okay, and so the links are not there, okay. Moreover, what we were doing when you had like two Gaussians was to consider the concatenation. Okay, we had two Hilbert spaces, H1, H2, and we consider phi of x, which is phi of x1, x2, as being phi of x1 and phi of x2. Okay, so concatenation. This corresponds to taking the sum of kernels. But it turns out that if you want to do things like in a proper generality with all results that extends, you have to replace the sum of kernels with the product of kernels. And that corresponds to replacing the concatenation of features by the tensor product of features. So now what I have is if phi1 is of dimension d1, phi2 is dimension d2, I map big thing in dimension like phi1, d1 times d2. And now what I have a covariance operator on the joint space. I have one on the single space and the other one on the other single space. And now I can try to use my information theoretic quantities to see if they mean something. So you can define the mutual information, which is the Kullback-Leibler divergence between the joint distribution and the product of marginals. And you can do this with our kernel operators. And what you could show is that it's non-negative, that's direct, but it's equal to zero if only if you are independent. Okay. And for what we had 20 years ago, we also had that, but this was not true beyond the two-dimensional case. So we can extend to all number of components and could define the mutual information in the multivariate way, and this is still true, and this was not true for what we had before. Then you may try to also characterize conditional independence, and this is where things break down a bit. So I won't have time to talk too much about it, but this is where things break down. Okay, and so we have some form of a data processing inequality. So if you marginalize, you lower the relative entropy, but we cannot say that it's equal if only if the conditionals are equal. So that would be something. Right, but what I want to finish on is on the use within probabilistic inference, and this is through duality. Okay, so one, I've already mentioned it earlier, is that why do we like so much, but do I like so much entropy? Because it has a very rich convex duality structure. And this is what is written here, is that if you take essentially the Fenchel conjugate of the Kullback library with respect to the first argument is a log partition function. Okay, so which means that if you take any function f, you look at expectations of f under p, minus the Kullback library divergence between p and q, q being a free distribution. Then if you optimize over p, then you obtain the log partition function, which is the log of the exponential of e of f of x dq of x. It's often called it's a normalizing constant of the Gibbs measure. And so this is used a lot within like probabilistic inference. And you can look at the book by Martin Wainwright and Mike Jordan. And so, whenever you need this, you can access it through the Kullback library. And now, since we have lower bound on this, we obtain upper bound on that. Okay, so essentially, whatever I described will provide upper bounds on the log partition functions. And when I have conditions under which this is tight, you get conditions under which this will be tight as well in the other setup. So this is direct. You replace P and Q, okay, by D of sigma P, D of sigma Q. And this gets really powerful if you take functions f, which are quadratic forms. Okay, so quadratic forms, then these expectations only depend on the trace of h times sigma p. And now this one can be computable by semi-definite programming. Okay, so here, this is convex in sigma p, this is linear, so it's a convex problem, but you still have to be able to solve it. It's convex, you can solve it, and you can look at the paper to know a bit more. Okay, so here I'm just like showing that you can extend all of that to variational inference. So simple example, okay, 1D, so just to show that you can solve that problem in simple cases. So I take a simple f in 1D, I get a value for the log sum x functions, and I'm taking phi of x, which is like a finite basis here, and I increase the number of basis elements here. And I take various sigmas, okay, and I always get upper bounds. This I know. And as I get more and more frequencies, I converge to the true log partition function. Okay, so just to not verify, but illustrate the fact that we get upper bounds. All right. So one thing which is interesting, and is in fact the motivation behind that work, is to add a temperature. Okay, so it's classical to add some temperature epsilon. So if you put an epsilon over there, then you replace the classical log sum x function by epsilon log of f over epsilon. And it's known that when epsilon goes to 0, so this goes away, this will convert to the maximal value of f, and that log sum x will convert to the maximal value of f. Okay, so this is in fact, people often use this as a way to smooth the maximum. Okay, question is, do we get similar things for kernel entropies? So let's do the same. You add a parameter epsilon here. And now you can play around with convex duality. So I won't do the details here, but you can check that. You get the convex dual of that. You see a log sum x function, but in the spectral way, and that kind. And when you let the parameter epsilon go to 0, you end up with an explicit limit, which is the infimum of the largest value, the largest eigenvalue of m, whenever you can represent f as a quadratic form. Okay, so this seems like hard to interpret, but in fact, there's a strong interpretation for that problem. And let me check how you can interpret this. So I'm going to assume that the features are normalized, okay? And by just playing around with the definition of lambda max, okay, and I won't do the details, so you have to trust me on this one, is that I can can show that this is equivalent to minimizing C such that f of x can be represented as C minus phi of x A times phi of x, okay, when A is PSD. So here, what do I have here? What I have here is a so-called sum of square relaxation of the maximization of f. So I knew that for the regular entropy, this was like an approximation of the maximization of f. So this should be related to the maximization of f. And it turns out it does. So you say f is C. So that quantity is positive, okay, because A is PSD. It's a sum of squares, okay, because A is, if you take the eigenvalue decomposition of A, you get a sum of squares. So f is C minus the sum of squares. So f is less than C, and you try to minimize C. So here, what I end up doing is I'm trying to minimize an upper bound on f, okay, where I replace C minus f being positive by C minus f being a sum of squares. Okay? And so this shows that what I'm presenting today is the probabilistic version of sum of squares, okay, with log sum x instead of full maximum. And the kernel thing, we did work on it with Alessandro Rodi and Ulysse Mato-Ferret. But of course, this dates back to Lasser and Pario and many other researchers. So if you want to know more, you can look at the various papers. So if you like sum of squares and you like probabilities, this is for you. All right. A few extensions before finishing. So what I learned in my PhD with Mike Jordan is that if you have a lower bound, you should try to maximize it. Okay, it's the beauty of lower bounds. Okay, the beauty of variational inference is that you optimize the bounds and you always make progress. Okay, so this is, can we do it? Can we do it here? So we have sigma p, sigma q is a lower bound. So you want to maximize. Okay, and what can you choose? You can choose a kernel because sigma p is the expectations of phi transpose. So if you take another phi, which is normalized, you maximize, you get a better one. Okay, and a bit of magic here. It turns out that this quantity is concave in the kernel, and so it was a well-defined problem. And in fact, full disclosure, I thought it was convex, and while showing convexity, I in fact use Jensen in the incorrect direction and prove convexity, but in fact I had proved concavity. Okay, so just like be careful. Okay, sometimes you end up using Jensen in the wrong way. All right, so it's concave, so now you can maximize it. And for example, if you have some known features phi of x, you can try to rescale the features with the PSD matrix. And now the kernel is it's a linear parameterization of the kernel, phi of x, lambda, phi of x. You need to check that this kernel is still like bounded, but it's still a linear constraints in lambda. And you can maximize that quantity in lambda. And this one is convex in lambda. Okay, so this one is not, okay, it's not trivial to me. This is convex in lambda. It is convex in lambda. Okay, and I provide algorithms in the paper. And if you do that, in a simple simulation, you do converge quicker. Okay, so if you compare to the entropy estimate with a fixed sigma, okay, like in blue and red, and you optimize the kernel, you do a bit better. Okay, so it's just a way to it's a way to learn a kernel. The good thing is that in many applications of kernel methods, you always have the choice of kernel, which is always annoying. Okay, and here we know we can choose it by maximizing the lower bound. All right. Let me skip that. Let me talk about a few extensions. First, if you don't like KL, I don't know why you should not like KL, but if you don't like KL, then this can be extended to all F divergences. So this includes KL, the square Hellinger, Pearson, K-square. Everything works the same. Now, if you know about quantum information theory, okay, I didn't know before starting this work, and some colleagues told me that there are better divergences than trace of log A minus log B, and which is always higher. And since we look at lower bounds, always higher is always better. So we can also use that as quantum entropy. And let me skip that. So you can look at the paper to know more about this. Okay, so to conclude, I like to so I try to present how you could use the classical moments formulation to have direct relationship with information theory and in the form of a lower bound. And so this allows us to get lower bounds for the entropy, hence upper bound for the log partition function. So as I've mentioned earlier in the talk, it's not ready for deployment yet in large-scale applications, okay? And so we're currently working on, so large scale here is a bit like overselling. It's like reasonable scale algorithms. But to me, what I like in the fact that this open up the machinery of information theory with well-defined bounds to many types of data. So I have like a few preprints and a blog post, and at this, I will thank you for your attention.
Thank you so much for that. So a quick update that you've been hearing a bit about. This is not one of the stated locations of protests on campus as far as we had known. However, that has changed. They have a right to be there. That is the current situation, and they had expressed interest in staying there for a while. So we will attempt to carry on as best as possible. So thank you all for your patience, and there will be a bar later today.
More free drinks for all participants.
Yep. So with that, I would like to open up for questions, and we do have microphones so that we can hear each other and that Francis can hear us as well. So if you have a question, then we'll bring this around.
Any questions?
Really feels like France now. Nice.
Hey, thank you for the very interesting talk. I have a question on the kernel learning that you presented at the end. Mm-hmm. Don't you risk, if you optimize for the kernel, isn't the best kernel the orthogonal one, where every feature is orthogonal to every other feature? Because it's the best lower bound because you get the k out. So don't you risk going there and then you're cursed by dimensionality?
Very good, Florentin. Indeed. So, of course, since we have a lower bound, if we maximize it, we end up with a orthogonal embedding, but then you typically do it with a constraint. Okay, so you have two types of constraints, and either you have an explicit feature size which which you don't want to go above because of computational limits, or because if you estimate from finite data, you don't want to go into overfit if you estimate things from finite data. So this is where this is true if you want to estimate, but for the log sum x function, so for entropy, I agree. I lost my. For entropy, I'm losing more. For entropy, I cannot go back to my. So for entropy, I agree, but for log sum x, for this one, okay, it's not the case. Okay, for this one, it's really a computational law. This one, a computational constraint. Okay, so you're going to add as many features as you can to get closer. Okay, and so typically you have a computational constraint, number of features, and with a given number of features, you want to do as well as you can in terms of value. Yeah, so, but you made the valid point. Yeah.
Okay, thank you.
Any more questions? Yeah, René. Hey, Francis, thank you. Great talk. One of the constraints you need to impose is that the PDQ is larger than alpha, and when you approximate with finite data, the 1 over alpha shows up in the bound. Can you explain what is the meaning of the constraint and why it's needed? Naturally,
okay, so
P is equal to Q, right? You have alpha equals 1, but beyond that, what are cases where alpha would be very small, and why is that a problem?
No, that's a good point. Let me one thing. Look, I'm using a power, but anyway. Let me just. Émile, peux apporter le chargeur? Le chargeur, oui. Sorry about that. Yeah, so I think the first thing is that whenever you want to estimate entropy, you always have an issue with the density alpha. The density, you always have to, at one point to impose the lower bound alpha, at least in the algorithm. And the key is the dependence on alpha. The key is the dependence on alpha, and so here, if dp of the q can be 0, you can add alpha, okay, and then you get a worse rate by optimizing the alpha over there. Okay, so it's a classical way. The classical way of dealing with it. Okay, so here I've not tried to optimize the alpha dependence. But I know that paper which I've mentioned, I think this one, they go at quite extreme lengths trying to take care of this like small alpha thing. But that's a good point. This to estimate entropy, you need this alpha to be extremely positive, but keep in mind that this is a relative Q. Okay, so if you have the good support, you're fine. But I agree, this is like a limitation, but like all entropy estimation frameworks.